completed.
Just a moment, okay? Okay, let's.
Sorry, I did something wrong. So you have to wait for a few minutes, okay?
Okay, is it okay now? Do you hear me?
I hear, but
Yes, yes.
But you didn't share.
What is the problem? Tell me. Do you
have
hear?
you started
You cannot
sharing?
see the screen.
No screen.
Oh, okay. This is my fault, sorry. Is it okay now? Yes.
Yes.
Okay, so sorry about this. Okay, so today we continue discussing what we started last. So my program of the week is the following. So today I will continue just giving you a little bit of theory. So by considering time-dependent perturbation theory. And tomorrow we will continue doing some exercise in time-independent. Then on Thursday, we will do some exercise with also including time dependence. So I just recap what I told you last time. And so what we are going to describe today is, so now the pen does not write. I'll try, just give me one second. So everything is going. Sorry, today everything is going wrong. I don't understand why. So I hope it will work now. Okay. So what we are going to do is time-dependent perturbation theory. Okay. So I hope we manage to start. So it's time dependent. Perturbation theory. Now, in the case of time independent, the goal, I just repeated, was the following. We have an Hamiltonian H0 for which we know the eigenstate and eigenvalues, and we are able to determine the approximate eigenstate and eigenvalue of an Hamiltonian which differs from H0 by small terms, I mean the lambda v. Now, in the present case, we have a different problem. So suppose that you have the following. Suppose that we have a generic time-dependent Schrödinger equation, which is H0 plus lambda v. And now what is important that this is v of t. So v depends on time, okay? Now, if v depends on time, if this v depends on time, then of course, talking about eigenstate and eigenvalue does not make sense. So what we want to determine is to determine the whole time evolution of psi of t in the presence of the full, governed by the full Hamiltonian. But somehow we have to find approximate approach as in the previous case. So what we do is to follow similar strategy. So the strategy that we followed in the time independent case was the following. We know what happened with H0, and we try to generalize and just construct step by step by including higher and higher order in lambda. Okay, so what is the similar strategy here? So let me write the solution when lambda is equal to 0. This is something I wrote last time, but it's good to recap. So I want to know first the solution for lambda equals 0. So I just remind you, the problem is the following. I have an initial value psi at times t equals 0. For simplicity, we just take the initial time t equals 0. And I want to determine the evolution psi of t. Okay, so the easiest way to write down the time evolution is the following. I just write, I mean, since I know, so if I have the following, so remember that H0 is time independent, so I can write down the eigenvalue equation, which is H0 phi 0 phi 0 of n. Okay, now if I know the eigenstate, then for sure, since these form a basis, I can write psi at time 0 as a linear combination of phi 0. So let me write psi at time equals 0 as sum over n of Cn, these are numbers, complex numbers, Cn phi 0 of n. And if I would like to know what is this Cn is nothing else than the scalar product of phi 0 of n psi t at initial time. Do you agree with this? Hello?
Yes, yes.
Okay, I want to hear also the others.
Yes.
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 Okay, very good. So if you have this, the wave function expressed in terms of phi 0 n, then the time evolution is particularly simple, because you know that psi of t is just equal to E, this you told me last time, okay, EH0. Julia, is Julia connected? I don't know.
Yes, I am.
Okay, so the answer is yes. Okay.
Yes. Thank you. I wanted to just confirm that we didn't leave her behind.
Very
Yes.
good. Thank
Yes.
you very much. Okay. So H0t applied to the state psi at time equals 0. Okay. Now, if I use this representation here, then the evolution is particularly simple, because this becomes sum over n of Cn e to the minus I H0 t. So I just put a hat saying that up to now it's an operator, okay? So you just remember that this is an operator. Psi, sorry. Cn exponential and then phi 0 of n. But this operator applied to this state is simple to calculate, because these are the eigenstate of H0. So this is equal to sum over n over Cn e to the minus I E0 n of t phi 0 of n, right? Okay. So when lambda is equal to 0, okay, so this is the case lambda equal to 0, the evolution is nothing else than expressed in the basis of H0 is a set of coefficients. These are time independent, okay? Times an exponential times phi 0, okay? So what is the idea of perturbation theory? I mean, the idea of perturbation theory is more or less that we have to start from what we know when lambda is equal to 0. And what we know is such a form. So when a good idea would be the following: if lambda is different from 0, then psi of t we can always write in this form. In particular, what we do is just to do, we look for a solution of the time dependent Schrödinger equation in a similar form. The only thing which changes is that now the coefficients are not anymore numbers, but are complex numbers dependent on time. Okay, so I want to stress that this is an equal sign, because as long as you do not, I mean, you just leave it open, the determination of this Cn, then this is always a possibility to write it, okay? The reason why you just use this basis and this exponential is that you know that when lambda is equal to 0, these coefficients are time independent and are just given by the overlap of the initial wave function with the basis phi n, phi 0 of n. So the idea is that starting from that situation that you know, you may construct a set of equation that determines the Cn of t. Now, I stress once more that so far what I did is exact. Okay, so I can always write this way. The only reason why I do it is that the set of equations that will come out of this particular representation are suited for perturbation theory. Why this is so? So let's continue. So I just rewrote psi of t is equal to sum over n of c n of t with the exponential a0 of n of t phi 0 of n, and I remind you that the solution that we have to, the equation that we have to solve is this one. Psi of t is equal to h0 plus lambda v of t psi of t. Okay, so what we do is just we plug this expression here and find what are the set of equations that the coefficient Cn should obey. Now, this I did it last time. Should I do it again, or I can copy the result?
Copy the result.
Just copy.
Okay, good. So basically, I just plug this in this equation, and then I just multiply from the right, from the left by phi 0 of m, and then I get a set of equation for the coefficients, which is the following: d dt of c n of t is equal to lambda sum over m of phi 0 of n v of t phi 0 of m. Then I have e to the I just call it omega n m. I just specify in a second what it is. C m of t, and omega n m is equal to e 0 n minus e 0 m. Okay, now you see that solving this set of equation is very difficult in general, if not impossible. Okay, because so this equation here, because it's a set of infinite differential equation. Okay, so it's not something it's easy to solve. Here is where perturbation theory enters the game. Okay, so far what I wrote is exact, but this set of equation is as difficult as the initial Schrödinger equation. This is nothing else than just rewriting the same problem. Instead of using operators, we are just using matrix representation. Okay, now let's see now how we can use perturbation theory. So for simplicity, this we call it VNM of t. Okay, now perturbation theory will be used by saying, look, I just seek for a solution of Cn of t as C0 n plus of t, sorry, plus lambda C1 n of t plus lambda square C2 n of t plus da 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 da. Okay, so we just seek a solution in powers of lambda. Okay. So here we are just using perturbation theory. Now, you see that, look here. Here, in the same way as we did it for time independent, you see that basically we just substitute the solution and then we just equate same orders in lambda, okay? So this means that here we are going to do the following, right? So we just have I, and then we have C0 dot n plus lambda C1 dot of n plus da 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 is equal to lambda sum over m of v n m e to the I omega n m t with the same series expansion C dot 0 of m plus lambda C dot. Yes.
Sorry.
Yes.
I think there should be no dot in the.
There is no dot. Sorry, I was copying in a wrong way. Yes, you're right. One plus lambda square C2 m da da da. Okay, so you see that now the right hand side of this equation starts with order lambda, while the left hand side starts order 1. Okay, so the first equation, I just, instead of dot, I just put it, I just put C dot 0 of n is equal to 0. Okay, this is 0 order. First order is lambda C1, so I have C dot 1 of n is equal to sum over m v n m e to the I omega n m t C0 of m. Second order, you can do it. I mean, it's just C dot 2 of n is equal, okay? It's just the same with the C1, okay, of m, okay? So in general, what you will get is C dot of q will be connected to C of m of q minus 1. So you can start solving the first equation. So you start solving the first equation, then you get the expression and you put it here. Okay, and then you can continue this way. Now, can you tell me what is the solution of of the zero order solution, the zero order term.
You mean the first order, or?
That's the zero order. C dot 0 of n equals 0. What does it mean?
It's constant.
Okay, but so these are what? What are the constant? These are actually,
The
what did I write here? These are the constant. Okay.
yes.
This Cn here. Okay. Now,
So C0 is equal to Cn.
yeah, this is because Cn is nothing else than the solution with lambda equals 0, because so in this new language, this is Cn, C0 of n. Okay. Please say yes or no.
Yes.
Yes, yes.
So what I want to say is that this is something we know. Okay. It's just a quantity which depends on so let me write it directly. This is C0 of n is just equal to phi 0 of n psi at the initial time. Okay. Now, once you know this, then you can put this and put it here and solve for the first order equation. Okay. So what is the first order equation? We just write it here. Okay. So we have just to integrate C 1 n of t is equal to minus I, the integral between 0 and t of tt prime v n m of t prime e to the I omega n m of t prime c 0 of m, which is constant. Okay. So you can determine C1.
Professor.
Yeah.
Is that the index of the V is NN, or the?
Sorry?
What is the
NM.
Oh,
Okay.
NN. Okay.
Sorry. Let me do something. Yeah. Okay. So let's consider in particular a given situation. Okay. So is this clear? I just integrate this equation. Okay. Where these coefficients are given. Now, let me consider one particular case in which I start from a given eigenstate of the initial Hamiltonian. So I just take C M0. Yeah.
I have a question about where is the summation?
But I simply forgot here some over M.
Okay. Thank you.
Okay. CM0, I just take it as delta mi. So this means I just prepare the state in a given eigenstate of H0. Okay, so prepare the system in an eigenstate of H0. Okay. Now, what is the subsequent evolution? Well, you just apply this formula and it is immediate. You just get C1 of n is just equal to minus I integral between 0 and t of dt prime v n I e to the I omega n I of t. That's it. Okay. So this means the following. Since, okay, but I'm just discussing for this particular case, but it means this is something which is quite general. Since the even if you prepare the system in a given eigenstate of H0, since you have time-dependent term, then the state of the system will have components also in all other states of the basis phi 0 n. So for instance, if I ask you, what is the probability? So you just do a measurement, okay? Now, suppose that lambda is equal to 0, equals 0. If I ask you, you just prepare the system in the eigenstate I. What is the probability that after a given time the system is in the state I when lambda is equal to 0? So this is a question for you. Hello? Is the question clear or should I repeat?
Can you repeat?
Yeah. So suppose that lambda, so I just write it, okay? So it's a question. Suppose that lambda is equal to 0, okay? If you prepare the state psi at the initial time in phi 0 I, okay? At later time, after some time, what is the probability that the system is in the eigenstate I? Okay. So tell me, how do I define the probability that the system is in an eigenstate I?
Number state in after, so number
Very good.
state
So,
in this generation.
so I just write psi of t. I think you're telling this psi of t phi 0 of I, and then I take the modulus squared, right?
Yeah.
Okay. So can you tell me the result for this particular case?
I think it's 1 because I don't know. Is it connected to the previous one that you say CM0 equals to delta MI? So
No,
I mean,
it is connected, but
yeah.
just
So
so it's 1.
yeah, I think it's 1
It's 1.
because
Why
it's
it's 1?
delta. Because CM0 is equal to delta MI.
It is 1 because the evolution of, if you start with this state, the evolution in this particular case will be just given e to the minus I E0 I of t phi 0 I, right? So there is only phase factor. So the probability will not be modified, okay? So if you prepare a system in a given eigenstate, then it will remain there. Now we want to do the same thing for lambda equal different from 0. Now for lambda different from 0, so I want to know the probability, the same thing, okay? That is psi of t phi, sorry. So let me write in a more complicated way. So I have psi of t equals 0, and then I take the modulus squared. Oh, okay, sorry. The modulus squared. Now, I know what is psi t equals 0. I told you I'm just taking at initial times psi of t, and initial time, this is phi 0 I. Okay. Now, can you tell me what is the solution in first order perturbation theory? Let's see if you just get it. I mean, otherwise we discuss. So I just come here. So you should look at this expression here. This one and this one. So in first order perturbation theory, so in zero order, we just saw that this is what you said, that C0 is just a delta function, okay? Which means that you are going to find always the system in the same. Now, in general, let's compute this, okay? So what is psi of t? Psi of t is sum over m of c star m of t e to the I omega n m of t phi 0 of m phi 0 of I. Do you agree? Hello?
Yes, yes.
Okay. So what is this? This is just a delta function. Okay. So sorry. I did something wrong. Sorry. I'm not sorry. This is completely wrong. So I need to erase because so this is wrong. Sorry. This is completely wrong. So I apologize. I got distracted and I should apologize. Pi of t is what? I have to compute the probability that I have phi 0 I psi of t. Okay. What I said, so what I wrote before, it was wrong. So this is the probability to find the state psi in phi 0 of I. Okay. I apologize for the mess. Is it okay now?
So how is then what about the first we answered at lambda 0? The one you erased, I think you erased it.
Yeah. So should I write again for lambda equals 0?
Yes.
Okay. So I take lambda equals 0. Okay. So the initial time, at the initial time, psi at t equals 0 is just phi 0 I. So I just prepare in this state. Then the question is, what is the probability P that the system is found in I, for example? Or let's do it more general, okay? So what is the probability that the system is found in M at later time? Okay. So the definition of the probability is that I have to take the scalar product of phi 0 of M with psi of t, and then take the modulus squared. This is equal, if I substitute the solution for psi of t, okay, this is equal to phi 0 of M e to the I e minus e 0 of I t phi 0 of I. And this is just delta M of I. Okay. So the probability to find the state in the system in the state I is 1. The probability to find in any other eigenstate is 0. Okay.
Yes.
Now I want to do the same. I want to write it here so that I have the expression for C1. Okay. So I want to answer the same question for lambda different from 0. Okay, so again, I just prepare the state in psi at time equals 0 as phi 0 of I. And then I want to know the probability that the system is, we find in the state M at time t. This, as I said before, and what I wrote before is wrong, okay? So I just have to take psi of t phi 0 of M modulus squared. Okay? Now, what should I do? I need to just to plug in the...
Sorry,
Yes.
I think you rewrote it wrong, right? It's PM0.
No, I think this is correct. Because I want to know the probability that to find the state in M, in phi 0 of M. So I have to do the scalar product of the wave function with phi 0 of M.
Maybe she means that the bra must be signed PM 0.
What?
It should be phi M 0 and psi t.
No.
It's in reverse.
No, in time. So actually what I wrote before, it was, let's forget about what I read before, because it was not completely wrong, but it was confusing. What I want to know is that the system at time t will be in the state psi of t. Okay? Do you agree?
Yes.
Then I want to know what is the probability to find at time t the system in one of the eigenstates. Okay? So I have to take the scalar product of psi, or let me write this way, but it's the same. So psi of t with phi 0 of m. This I have to take the scalar product and then take the square. Okay? Is this
So
clear?
why is the case of lambda equal to 0 is different?
No. It's not different. It was, I just wrote exactly the same, but simple. So let me, okay. So let me do it. So when lambda is equal to 0, psi of t is just phi 0 of I. Okay? I just redo it. Okay? So let's see. So psi at time equals 0. So this is lambda equals 0. Is equal to phi 0 of I. Okay? Now, can you tell me what is the evolution for at later time if I start from this state?
Times the unitary operator.
Very good. So it's just e to the minus, which applied to the state is just e to the e0 of I t phi 0 of I, right? Okay,
Yes.
good. Then, so for instance, I want to know the probability that the system is in the state m different from I at later time. Then I have to take psi of t phi 0 of I. Okay, and then take the modulus square. Okay, let's do it. Now, this is a phase factor, so it disappears from the modulus square. So the only thing I get is phi 0 of m, phi 0 of I, modulus square, which is equal to delta mi. Sorry, since I am asking m different from 0, this is 0. Okay? Hello?
Yeah, so it's equal to 0, not 1.
No, what does it mean is equal to 0, not to 1?
No, because before we wrote, before we calculated.
Before I ask the probability that this is in I. If I just the probability that is in, so instead of m, the probability that is in I, this is I, and this is actually 1, okay?
Yes.
Okay? Which means that you prepare the state in a given eigenstate, it remains there with probability 1. Is this clear?
Yes.
Okay. Now I want to ask the following, the same question for lambda different from 0. So I start from phi 0 of I. Okay. So the probability that I will find the states, the system in M is just given by psi of t phi 0 of I modulo squared. Okay.
Yes.
Okay. So let's consider this M different from I. Now, since we said that psi of t has the form of sum over M over C M of t e to the minus da 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 phi 0 of M, right? This is the form. So when I do the scalar product, the only thing which matters is just this is equal to sum over M over C M of t modulo squared. Right?
Yes, yes.
Okay. So I just put this and take the square. Now,
Is it CM star?
What's the, sorry, Professor, what's the preparation again? It's the
it's this
same.
one. Yeah. So to simplify things, I just call it this L. Okay. So that not to confuse you. Okay. L L, and the preparation is this one.
I said, is it CM star?
What? It's modulo squared, so it's the
Conjugate.
same. Huh?
Yeah.
Okay. So you're right. If I write here the star is the same, huh? Because I have to take the modulo squared.
Yes.
Okay. So I have to take this. Now, what is the solution of this question in first order in perturbation theory? Okay. So first order in perturbation theory, I have just to plug in I have to determine the first order correction. Okay. So I should stop in solving the time dependent perturbation theory at this order here. Okay. And then I can I remind you that C0 of n is just delta ni, C1 of n is this one. I just plug it there and solve it. I have to do the sum. So this is just, I remind you, C0 of L plus lambda C1 of L, and so on and so forth. Okay. I take the square, and then I just determine what is the probability that the system is just found in the state M different from 1. Well, this is nothing else than C1, because the 0 order, there is no possibility to jump to another eigenstate. So this probability m different from I of t to first order is nothing else than lambda square. I take lambda equal real, okay, for simplicity. We can do it with lambda complex, but we have to write the Hamiltonian in a slightly different way. So this is nothing else than just the C1 squared t dt1 v n I of t prime e to the I omega n I t prime modulus square. So this means that when you have time-dependent perturbation, there are possible transition to other states, and if you want to determine the probability to have this transition, then, for instance, in first order in perturbation theory, then this is just the solution. So let's apply this expression to a very simple problem that is the following. Suppose the following. So I have H0 harmonic oscillator. And then you apply a transition, which is a perturbation, which has this form: lambda v of t is equal to q epsilon x e to the minus t square over tau square. This is nothing else than the electric field applied to this kind of harmonic oscillator, which is switched off and on and off in time. So if you have this is time, so this magnetic field is something like this, okay? That is off in the past, in the distant past, and will be off in the distant future, okay? So how do we do perturbation theory? Well, it is the best is to write lambda v using the creation and annihilation operator, which is something q epsilon e to the minus t square of over square. Then you have L over square root of 2. And then you have A plus A dagger, okay, from the X. Now,
Professor,
yes.
Why you don't have lambda on the right hand side?
I just call lambda v in this form. So this would be my lambda, okay?
Oh, okay.
But it's irrelevant. So I'm assuming that the small parameter is the electric field, in a sense. So I just call this the whole lambda v, this term here. Now, basically, then what I have to compute are the matrix element Vni. So I have to compute phi 0 of n, A plus A dagger, phi 0 of I. Okay, tell me, what is the, so if you start with the ground state, if I is the ground state, I is 0, okay? So what is the only matrix element different from 0? From this, sorry, I did not hear.
N equal to 1.
Very good. So the only different, it's n equal to 1, okay? N equal 1. And so if you assume this perturbation in first order, the only possibility is to have transition to the first excited state. So let's see. So I have to plug in this expression here inside here. Okay. Now, and then I have to do this integral, supposing that I take t0 going to minus infinity, and then as a function of t. Now, I want to know, okay. So I want to know, if I ask you the probability when t is going to infinity, okay? If I want to know the probability when t is going to infinity, then I have to do the integral between minus infinity and plus infinity of dt of e to the minus t square over tau square e to the I omega. In general will be ni, okay? In this case, it's just h bar omega or omega, okay? It will be just I omega t. These are Gaussian integrals, which are known, and the result is e to the minus omega square tau square over 4. And then I have to see what is the numerator, which I do not remember. Yeah, so it's pi tau square to the minus 1/2, okay? Now, this is the result. If I plug in the expression for C1, I find one result which is interesting to discuss, and that's why I would like to discuss. So this is Pn of t going to infinity is equal to delta n1, okay? So there is a probability, since it's to first order in perturbation theory, this is just a probability to go, is different from 0 only to go from the ground state to the first excited state. Then I have some coefficients which are not very important for me, but I will comment on this. Tau square to m omega. So all this m omega comes from the m comes from the L, okay, the oscillator length, and then I have n to the power omega tau square over 2. Please wait for me just a second. I have to do something, okay? Just a moment. Okay, so what can we learn from this expression? There are interesting things. So the first thing, as I said, is about this term here. This term here is just a result of perturbation theory. First order perturbation theory, the only possible transition is just to go from the ground state to the first excited state. Something similar would have happened if you would start from any excited state. However, there you would have two transitions to the n+1 or n-1. Now, another thing is just this E squared. E squared is again a probability. So first order, it's the correction is order of epsilon. As I said before, it's like having epsilon is lambda in this case, and this is so this probability is L squared. Now, the interesting thing that I would like to really stress is this exponential. Now, suppose the following. Just notice that if tau becomes much larger than 1 over omega, okay, this exponential goes to 0. So what does it mean that tau becomes large? So let me just draw it in a very sketchy way. So the perturbation is something like this, okay? Or it can be something like this. Okay, do you see the two curves? So this more gentle curve is a larger tau. Are you with me or not?
Yes.
Yes, we are.
Very good. So you see that if the perturbation is more gentle in time, so a change in time is lower, this exponential becomes smaller and smaller. Actually, when the scale of change, of time change of the perturbation is larger than 1 over omega, then all the transitions are suppressed. Do you see this? I'm going to comment on this, but first tell me if you see this in the formulas, in the expression.
Sorry? Why do you compare tau to 1 over omega?
Because in order to have this exponential to be 0, then I need omega tau. Forget about the 2, okay? Is much smaller than, much larger than 1. So I've always to compare tau to 1 over omega. Okay? 1 over omega is the natural frequency of the oscillator and fixes a time scale. Tau is a time scale which belongs to the external perturbation. Now, I would like to see what is the, I want to compare the time scale of the external perturbation to the natural time scale of the system. And I have two well-definite limits. One limit is the one in which I do, I perturb the system in a very gentle way. Okay? Which means that tau should be much larger than 1 over omega. And this way, you see that the transition, I mean, here we see it in the first order perturbation theory, but it's true in general. The transition to other states are strongly suppressed. Just imagine the following. Suppose that you want to push somebody, okay? So somebody is just standing in just in front of, I don't know, the queue to get the coffee, okay? And you want to, I mean, you are oh, I am unpolite and I want to push you because I want to coffee before you. Okay, so I can do two things. I just give you a big push, okay, and then probably you just may just fall just on the side, okay, but I just modify strongly your the state of your system. Or I can just push it very, very slowly. Not just I press it slowly, but I just do it gentle. I just increase the push in a very gentle way. So in that case, you expect that you're just moving, you're still standing still, but probably you will change the position of your equilibrium position. Or you just imagine that you have, okay, this is a simpler or probably a more clear example. Just imagine, do you see these headphones? Do you see them?
Yes.
Okay. Imagine that this is an harmonic oscillator, okay? So this harmonic oscillator. Now imagine that, okay, you need to have some imagination because this is not clear. Now, suppose that you want to reduce the length of the harmonic oscillator. You have, suppose that this is, imagine that this is in the ground state. You can do two different things. Or you just push it fast, and then you see that it starts oscillating, okay? It means you create some excitations. Or you can do it slowly, okay? Here it does not work, but just imagine that you do it slowly. Do you see that there are much less oscillation? Okay. Okay, so I just change the state of the system, but without changing, so without exciting to higher states.
So that's the reason why the probability.
Sorry, I do not. Can you repeat? I did not hear.
Yeah. Actually, I just want to confirm. So that's the reason why when we have the two greater than 1/omega, so the probability to go into the state inside the state one is go to 0.
Exactly. So the limit in which you do very gentle changes to the Hamiltonian is also called adiabatic limit. And in the adiabatic limit, so this is adiabatic limit, okay? And if you do, I mean, probably if we have time at the end of the course, I will just give some one lecture on adiabatic limit because there are interesting features there. But if you are in the adiabatic limit, the transition between levels are very strongly, are completely suppressed. Of course, there will be tiny effects, but they are suppressed. Okay. Is this clear or
Yes.
okay? Now let's go to the other limit. The other limit is when I just take omega tau much smaller than 1. Okay, if I have this, then this is almost 1, right? This exponential is almost 1. And this will be a number. Now, in principle, if you increase, so once you fix, so you see that, suppose that I just write, just to fix this, I can write here square and then I put omega. Okay. So, sorry, I want to do something else. So, let's leave it here. I mean, I want to do it, okay, this way, sorry. So I just write omega square, and here you have omega squared, okay? Now, suppose that I fix this much smaller than 1, okay? So this is 1, I can forget it, and I have this expression. Still, when perturbation theory is valid, well, perturbation theory is valid as long as all this cannot be of the order of 1. So this should be much smaller than 1, okay? So you should be careful. You cannot take this for any value of epsilon, because you see this probability, for instance, when epsilon grows, when the electric field grows, it may become even much larger than 1, which is nonsense. This is true in any case, okay? So not only the, okay? There is an interesting limit, other interesting limits. When omega tau is almost 0, then the probability is again 0. Okay, so what does it mean? So basically, when you take this expression for omega tau much smaller than 1, then basically this curve becomes sharper and sharper. Okay, and then you are entering in something which is called sudden limit. Okay, so one should be careful in doing it properly. But if you do a perturbation which is much faster than the typical time scale of the systems, then what happens is that the system has no time to react to the perturbation, and therefore it will not change the state. Okay, so suppose the following. Just in general, this sudden perturbation is the following. Suppose that you just switch the electric field suddenly in time. Okay, so this is epsilon of t, and you do like this. Okay. If the quantum state here was psi of whatever, psi minus, up to here, after the perturbation, the state is the same. Psi t minus will coincide to psi of t plus, meaning the system had no chance to change its state. Okay, so sometimes you will hear about this sudden perturbation, and you have to keep in mind. Now, since we have 10 minutes, then try to do the following. So solve the problem. So find the first order correction. So I just write it here. Find first order corrections to the state in the case in which the Hamiltonian goes like, so the perturbation is still an, so let's say, it's still an harmonic oscillator, and lambda of t is just given by lambda v e t over tau, and then you have to consider the system from minus infinity to t equals 0. So I would like to know what is the state at t equals 0. Okay. Suppose that the system started from so from the state phi 0 of n when t was minus infinity. Okay. So you can do the following. You just take, so first you just do the explicit calculation for the same perturbation. The only thing that you have to change is for the harmonic oscillator, the only thing you have to change, instead of having e to the minus t square over tau square, you just take this expansion, sorry, this time dependent. And then you try to get it for any generic situation. So any generic V. So you just assume that you have V n m of t is nothing else than phi 0 of n v phi. Oh, so if you, this confuses you, just put v0, okay? So it just phi m times e to the t over tau, okay? So this is something given that you don't need to know, okay? So find the first order correction to the state. Is this clear, or is the exercise clear? Hello?
Hello.
Yes. Did you
Yes.
get?
Yes.
Okay. I want to hear the other.
Yes.
Yes.
Okay, very good. Now, tomorrow we are going to do the following. We are going to study. I just want to, sorry, no, tomorrow we are going to do some exercises, as I told you, in time independent and also time dependent perturbation theory. And Thursday, we are going to consider a special case of time dependent perturbation, that is periodic perturbation. So we are going to consider V of t, which are like V0 cosine of omega t. Perturbation in time can be cosine, sine, whatever, exponentials. Now, you know that if you shine some radiation on atoms, when do you get, when you have transitions between levels?
When the energy applied enough
To excite the electrons to the next level.
No, well, yeah, but what should, so if you have a radiation, then what should match? So if you want to go from the first excited state to the second excited state of an atom, and you have some selection rules that allow this transition, how, so what you should do? I mean, what do you have to select? An amplitude, frequency, what in the radiation that you apply? What is important?
the energy difference.
So explain me better, the energy difference of what?
Between two levels.
Yeah, should be equal to what?
Equal to the energy that we apply.
So what does it
frequency
mean?
of the light. So the
Yeah.
frequency of the incident
So
light,
it's the frequency of the
incident light.
of the radiation should
Yes.
match the energy difference. Okay.
Yes. Yes.
This is important. Now, so far you just know this as a fact. Then we are going to see this by studying time-dependent periodic perturbation. We are going to see that when you apply periodic perturbation, periodic in time, then the transition will be strongly enhanced when there is a matching between the periodic perturbation, the frequency of the applied perturbation to the energy mismatch between the different levels. Okay, this is something we are going to do. I think
But also just to ask about this, which I think I asked Professor Santoro earlier on about the so-called Floquet Hamiltonians that is periodic with time.
yes.
If we do perturbation theory and all that is periodic is the potential, is that enough for the wall of the Hamiltonian to be periodic? Because in the case, if we do this in solid state physics, we have a periodic Hamiltonian, but based on K, or based on the
Yes.
yes.
Okay. Right.
Yeah.
So the answer is that what we are going to do is something which is much simpler than Floquet. Okay. So
yes.
Essentially, Floquet is the following. So let me explain. If so, suppose that you have an Hamiltonian such that the ht plus t is equal to h of t. Okay, it's a periodic Hamiltonian. Okay. Now,
Yes.
Floquet theory tells you that that basically the solution of the Schrödinger equation can be expressed using an eigenvalue equation for the evolution operator u of along one period. Okay, let's call it, I don't know, phi n of epsilon e, so e equal to e to the I epsilon phi alpha, let's call it alpha t phi alpha. Okay. So it can be expressed using something like this, where these are called Floquet eigenstate and these are Floquet quasi eigen energies. Now, what we are going to do now is just perturbation theory. Of course, if you do Floquet, which is something similar for those of you who studied the solid state physics, similar to the Bloch theorem, but not in real space, but in time. Okay, is much more complete. Okay, what we are going to do is just perturbation theory. And when we do perturbation theory, we are just using the as a basis the eigenstate and eigenvalues of the time-independent perturbation, time-independent Hamiltonian. So we are not doing Floquet. Okay.
Okay. Okay.
Now, if you're interested in learning Floquet, we can discuss. And I can give you some reference, or we can do it together. Okay.
Okay.
But what we are going to do is something much simpler. What we are going to do is just consider this as a perturbation and see how we induce transitions. Okay.
Okay. I appreciate to get more on this. Yeah. Thank you.
More questions? No. Okay. So are you still split in half concerning lectures with, so I think tomorrow I will do the lectures in room D, okay? Just to mix up things, and then let's see how it goes. So I'll talk to you tomorrow at 11, okay? Have a nice lunch and afternoon. Bye-bye.
Bye. Thank you.
Bye.
So thank you.